estimate the number of protein conformations N sub C, first, we think about the fact that it's going to be dependent on the backbone and the torsion angles that we had, phi and psi. They're going to dictate what conformations would even be possible in an unfolded state. So we had sort of talked about Ramachandran helped us decide when it folds up, angles that likely become alpha helices, angles that likely become beta sheets. In this case, the same thing is true with our backbone torsion angles. There are just some that aren't possible. Even when unfolded, things just aren't going to kind of hang out in that position. Okay? So the assumptions we make are that there are basically 3 conformations of equally low energy for the backbone, and there are 2 conformations of equally low energy for each side chain. So at each residue denoted by the alpha carbon, you have 3 backbone times 2 side chains, or 6 conformations. Again, these are just approximations that we settled on, and when you actually do this stuff experimentally, because you'll never really be able to count all the possible conformations, you'll get your entropy and your enthalpy, and really everything off of calorimetry, you realize the numbers make a lot of sense the way you thought they did. Okay? So these are good assumptions once you do it in a lab. But for a protein that is N sub res, so N number of residues long, then N sub C would be given by 6 conformations for the first residue, 6 for the next, 6 for the third, so on. So 6 raised to the number of residues in your chain is our approximation for N sub C. Fast. So if S unfolded was equal to gas constant times the natural log of the number of ways my protein can be unfolded, and I estimated this to be 6 raised to the number of residues in my chain, okay, I can plug that in, and like I said, this was just an estimation that turns out with calorimetry to be pretty good. R is the natural log of 6 raised to the number of residues. I can rewrite this as R times the number of residues times the natural log of 6. Okay? This is just for a logarithm of something that is raised to a power. You can pull it out in front. That's just a property of logs. Okay. So let's imagine that I have a 50 amino acid long chain. The entropy of the unfolded state, we'll use a standard state here. We're talking about, let's just say we have 1 mole in solution of, we have a mole of proteins, all of our 50 amino acid long proteins. This would be equal to 8.314 times nothing, joules per mole Kelvin. That's feeling Boltzmann. Times 50 times the natural log of 6. You should get 744 joules per mole Kelvin. Like I said, I'm at standard state. This is just for 1 mole of proteins in solution. So to calculate the entropy of unfolding my protein, it is just 0 minus 744 joules per mole Kelvin, okay? Or negative. My sign makes sense because I know that when it's not unfolding, I'm so sorry, folding. The change in entropy when I fold up, this is the folded state, this is my product. I'm going to this is my reactant. I started unfolded and I folded up. Apologies. I expect it to be negative. For my enthalpy term, I have delta H was equal to the change in internal energy plus the change in the pressure volume term. This was just our definition of enthalpy. This can be written as pressure times a change in volume plus volume times a change in pressure. This is 0, Y. Why is change in pressure 0? where is protein unfolding and folding happening? Inside of us where we are at atmospheric pressure. So constant P defines our biological systems. How come this is also approximately 0? The total volume of the protein is also not changing significantly. If I were to stretch it all out in one long line and try to take a volume of it as if it were some sort of cylinder versus if I then wrap that cylinder up, the volume of the actual protein itself, not how much kind of volume it is part of, but just that protein's volume doesn't change whether it's in a long line or curled up. Okay. Delta H is equal to delta U. Delta U, change in internal energy, was equal to change in kinetic energy plus the change in potential energy. Why is this 0? Isothermal. Protein unfolding and folding inside my body is happening at approximately constant T that I am maintaining. So delta H here is only going to depend on essentially the breaking and forming of bonds, or in this case, my non-covalent and secondary interactions, because I'm not actually talking about breaking the backbone of my protein when I unfold it. I'm just talking about breaking the interactions it makes. Okay. When I break, what's the sign of delta H? It takes energy, so it's positive. When I form new interactions, delta H will be negative. Okay. Another lovely assumption. Assume that each residue in a chain can make one favorable interaction upon folding. I mean, this kind of makes sense. Any one residue, once it starts to fold up, like that residue might participate in a disulfide bond or might participate in a salt bridge or van der Waals, but it's probably not participating in a bunch of those. So this is a pretty reasonable thing that when I fold it up, it's going to get to make one favorable interaction with something nearby. And the energy released, okay, and we say it's released because when we make an interaction, we're releasing energy. In that formation is approximately 3 kilojoules per mole of the particular residue. I'm still talking about a whole mole of proteins. If I were to actually try to think about the enthalpic contribution of a single residue, it would just be a really stupidly small number. Okay, so this is, I have a mole of proteins, and for one residue in the mole of proteins, that residue makes a favorable interaction and gives me 3 kilojoules of energy. The next residue gives me 3, so on. Okay. So I can calculate delta H of folding. Okay. This sort of implies my standard state here. It's going to be the number of residues long times we're releasing the energy, negative 3 kilojoules per mole per residue. Just a weird way to think about it. Okay. We said this was 50 amino acids earlier, right? I think we said, what about for 50 amino acid long chain? So this would give negative 150 kilojoules per mole. So if I plug all of these numbers in, delta G of folding at standard state for a 50 amino acid, for 1 mole of a 50 amino acid long chain of proteins. Delta H folding minus T delta S of folding, negative 150 kilojoules per mole minus 300 Kelvin times negative 0.744. Last, it was up there when it was 744, it was in joules. This is now in kilojoules per mole Kelvin. Kelvins drop out. If you do this math, you get positive 73.2 kilojoules per mole. And this is where we go, but wait, this is spontaneous. And so this was for when we consider just the protein. I haven't talked about what is happening with water.